Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. Today we are going to go into the third part of our lecture as part of the ecosystem for building the standard inverted index. I'm going to first summarize what we have seen so far. This is called the standard inverted index. So it has terms on the left. Then it has in the purple rectangles what we call the document frequencies, which is the number of documents that contain these terms. We'll get this smaller. And then here, so these are the document frequencies. Here it says that there are 6 documents, and these are documents 1, 2, 3, 5, 6, and 8, for example. And you see the in that case, we have 7 terms, right? These are the terms. You see, this is always the count of the blue rectangles here, right? So the size of the list. Is it me or is there no audio? Let me check. I think normally it's connected to the Herzal. What about everybody else on Zoom? Can you hear me? All right. So the sound works. Okay. So the next thing that we looked into is our first ever information retrieval system based on Boolean querying. And the idea is that we have a query that is in first order logic where we are looking for terms, and we have AND, we have NOT, and we have OR. As an input, we have a set of documents. And the output of a query is also a set of documents. It's a subset of the original set of documents. The set of documents on the left, that's called the collection, right? We have a collection of documents, and we are returning a subset of that collection. What is very important is first that this is deterministic. And second, the output is not ordered or ranked or anything. It's just a set, right? So it's not like in a search engine just yet where you have the top 10. Here, there is no such thing as a top 10. All right, maybe I can also remove the toolbar from the view here. I just need to click close again. All right. This is the context-free grammar that we are using for our language. So you see, it's pretty simple. The idea here is that we have terms, and we can combine them with not, and, or, and the not exp, and exp, and so on. These are called non-terminals. The grammar is arranged in the way that precedence holds, right? So not is the highest precedence, and then and then or, right? And is a bit like multiplication, or is a bit like addition, so and has precedence over or. Okay? So this we gave you for free in the exercise. I think it's this week, right? The exercise that is released today. And so that allows you to pass the queries, and then you can write the code that is missing in order to actually execute the query against an index. So if you look at the high level of abstraction that we have, we see, we look at a document in a simplified way. Normally, a document is a list of words. I mean, if you want to read a novel and enjoy it, it should be a list. But we abstract it as a set of words. We lose information here. We lose the order, and we lose the number of occurrences. And finally, we linearize the documents as vectors of Booleans, right? So the only information in there is that every word or term, if we use the terminology of the index, every term is or is not in the document. The 1 means that it is, the 0 means that it is not. So one way, there are several ways to look at this abstraction. So one way is that when we simplify the whole document and turn it into documents that are sets of words, what we get could be seen as a bipartite graph, right? So a bipartite graph is just a graph in which the nodes are in 2 categories. In that case, the documents and the terms. And you can have edges between the first and the second category. So for example, here, every document can be linked with a term, and the edge means it is in here. So an edge means a 1 in the vector, and no edge means a 0 in the vector. For whom does that make sense? Right? So this is a bipartite graph. Now, we have equivalent representations. It's all the same. Another representation is the adjacency matrix that we saw last week, where every document is a vector. I think it was, I never remember if I put it on the rows or the columns. I think the terms were on the terms were on the columns and the documents on the rows. It doesn't really matter. It's just a matter of convention, all right? But we have an adjacency matrix, and then we have the postings representation where we have the terms that are on the left. This is our inverted index, the terms in here linked with the list of documents that are in there. So every term here, now remember, corresponds to a row. If you have a 0, you skip, and every one, you include it in the list right here. Who now agrees and sees crystal clear that this, and this are equivalent representations? It's all the same. You can convert any to any other. Okay? On Zoom too? You can raise your hand on Zoom if you're following. Yeah, okay. Very good. So this is what we did last week. And now I will be even more precise today with the terminology because we will start diving into it. But just to be very clear and showing on these 3 visuals, because since they are equivalent, I can show them at the same time. This is a document. In the case of the adjacency matrix, it's a column, right? This column here is the same thing as this. Just here it was on a row, but you just display it as a column, right? So this is a document. And here, this is a document. Why did I highlight 3 different squares here and not just one? Yeah, exactly. You can have 3 different terms in the same document. So this is the same document here, but it appears every time there is a term that it contains, it appears. So this together is a document. Documents, documents, documents. All right. Then we have the terms. So these in the bipartite graph, these are the ones on the right. In the adjacency matrix, these are the rows. And in the postings, this is one entry, right? So the term here with its list, the list of documents. So this is a term. And third, we have what's called a posting. And I told you about this word, a posting. A posting in here would be an edge between a document and a term. It's the idea that this term appears in that document. Here, a posting would be just one single cell in the matrix, right? This term appears in that document. And here, a posting would be one single square. So this is why it's important to understand that this here is a document. It's the equivalence class. It's all the documents the postings that have the same document ID that are a document. And here it's really a single one of these. And here it's important to understand that even though these postings here, they only bear the document ID that we actually write in here, it is implicitly also containing the term that is here, right? So a posting is really a pair with a document and a term together, which is very visual actually here and here, the intersection of rows and columns. For whom is that clear? All right, term, document, posting. We'll throw more terminology today. Now, last time when we built the standard inverted index, I simplified a few things. I just went very quickly. We took a document, tokenized it with the spaces, and then we just grouped together the tokens that are the same and had the index. In reality, it's not that simple, unfortunately. And the goal of this lecture today is just to make you understand that reality is much more complicated than that. So I'm not going to give you a full solution of how to solve reality. If you're confused at the end of the lecture today, then that's great because that was my goal, kind of. I just want you to see that it's actually not easy. There's plenty of simplifying assumptions that we've made last time when we built that index. So in reality, we first need to collect the documents. That in itself is not easy. Imagine you want to build a search engine and you need to download the internet. Not trivial at all. Then you need to tokenize the documents. We oversimplified it by saying we just use the spaces. And whenever there is a space, we just cut. But in reality, it's not that simple. Then there is linguistic preprocessing. I will give you plenty of examples. But for example, the plural form, right? If you say lecture, lectures, it's kind of the same, right? In terms of index. If you look for one, then you would like to find the other. That's called linguistic preprocessing. And then you need to build the index. That's also not easy, especially when it's at large scales. In fact, it's so not easy at all that I will have a full week just on that, on how to construct the index when it's enormous. Very exciting, actually, to look at this. So let's just take things one after the other and make our way through all of this. So first, let's focus on document. What is a document? Last time I kind of simplified saying a document is a book, right? You have a library, a document is a book. But not everything is a library in real life, right? So we collect the documents. So the collection is a set of documents. Now, the first challenge is actually reading them. Because in the good old times, there was no computer. You have the book in your hands. So the very early systems, they actually started with metadata. The libraries, it used to be on paper, then it was done with computers. So what would the librarians do back then? They would take each book when it arrives to the library, and then they would record somewhere the title, the authors, the publisher, maybe the price, maybe a few keywords about the book, like a list of keywords that the book matches. What else? Oh, the Dewey classification index, right, for the clustering, so the code of what the book belongs to. And then, so in the 90s, let's say they would put it in the computer. There is actually software that is sold to libraries to do that. And then they would put on paper the 3 letters of the classification, maybe the first 3 letters of the author, and then bring it to the shelves, right? And then the people would come to the library, sit in front of the computer and type some search for the authors, for the title and so on. And this is how it would work. Before that, it was even done on paper. You actually built indices like the standard inverted index. That was actually done on paper. That takes a lot of time to actually do this. But the one thing they did not do is the content of the book indexing, the indexing of the content of the book. The librarians did not actually look at every single word of the book in order to process them. They would just, maybe read the book if they're interested and come up with keywords, but that's about it. But now, today, we actually do what's called full text search. We are interested in looking at what's actually inside. And today it's with the internet. So you actually look at web pages and PDFs and so on. And so actually you need to read it. So in essence, if you're lucky, that's going to be text. And if it's text, then it might be encoded in some way, like character by character. And here too, this is where the complexity begins. In the very good old days of computers, things were very simple. In the US, for example, in English, there are no accents or anything. So ASCII was some encoding that only needed 128 different code points, right? So it had the letters of the alphabets, the numbers, and so on. And then every single character was encoded on 8 bits, right? The problem is that very quickly, there was a limit reached as soon as you want to also encode French, German, Chinese, Hindi, and so on. So then you basically run out of code points. So ASCII was no longer enough. And then what happened next was actually very confusing and created a lot of problems. This is the ASCII table, by the way, but you're computer scientists, so I'm sure this you've already seen plenty of times, but this is what we had back then. No accents, nothing. And you encode a character like this in bits like this. Okay. Now, what happens is that's on 7 bits, technically, all the way to 0 between 127. If you go to 256, there is a bit of room. So for some languages like French, German, Italian, and so on, you can just add the accentuated letters with the remaining bit, right? That gives you 128 more possibilities. The problem is that that was done for many different regions of the world and in a different way. So there's all kinds of ISO. I think it's every time an ISO 88, I don't even remember the code exactly, 8853 or something, 1, 2, and so on. So there were many different encodings that were invented every time for a language. And that was for the European languages. because if you consider other languages like Chinese, Japanese, where the number of symbols can be even greater, then this is very challenging. But recently, we finally solved the problem. I mean, recently, now it's getting old, but we unified everything with something that's called Unicode in a way that it's an absolutely enormous catalog of characters, but it's universal. It has absolutely, well, the goal is to have absolutely everything in there. What is important to understand is that Unicode is not an encoding. It's only a catalog. It's a list of characters, and every character has some number. There's character number 1, character number 2053, and so on and so on. It has pretty much every letter that there is in every single language in the world. Maybe there are still a few that are still being added. And in fact, now it's so complete that I think that every update is a lot about adding new emojis, right? Which are actually also very useful. That's the catalog. So the catalog doesn't tell you anything about how to convert that to bits, right? That's just a list of characters that each have some number. That number is called the code point. Now, in order to encode, there are multiple ways. The most popular one is UTF-8. UTF-8 is one of the several ways that you can encode Unicode code points in zeros and ones. So let me show you UTF-8, how it works. It's elastic. That's the first thing. So the number of bits that you are going to use for every character changes. For the simplest characters, so the ones that are in ASCII, so Unicode is designed in such a way that if it's ASCII characters, then it coincides. So the number for the English characters actually is the same in Unicode and in ASCII. So if that's the case, that's character P here, and you need at most 7 bits. My less than should be understood here as not strict. Normally it's strict, it's just a mistake here. So up to 7 bits. What you do is that you put the 7 bits in here and you add a 0 in front, right? The 0 tells you there's only 1 packet, right? And that's the encoding in UTF-8 of variable length. A consequence of that is that if a document contains only ASCII characters, the Unicode encoding, the UTF-8 encoding, and the actual ASCII encoding are exactly the same one. This is why you can open and you don't need to worry about the encoding. Now, for the more complex code points, this is the letter pi, for example. The code point in base 16 would be 3C0, but it's really just a number. If it's up to 11 bits, so here it's exactly 11, no, there's a 0 more, so it's actually 10, but it's at most 11. What you do is that you put here, it's in black and bold, you have the actual bits of the code points, and in red, you have the additional kind of metadata. And the idea is that you put 110 in front of the first packet and 10 in first of the second one, right? So in that case, you have 2 bytes. You have 2 packets of 8 bits to encode just 1 letter. And when you read, you see 110, so you see that this is the first of 2 packets. And then you read the second packet, the 10 indicates that it's a continuation packet, right? So this is it, and then you can decode that to pi. Then there are even more complex symbols that came later, like the euro symbol. This is the number it has in base 16 in the Unicode catalog, up to 16 bits. Then you put here 4 bits here, 6 bits here, and 6 bits here. Now the first metadata, I don't know how to call that, let's say metadata, is 1110. That tells you that there are 3 packets. 110 tells you there are 2 packets. 1110 that there are 3. Then 1010, the continuation packets. That's how it works. So now you see this character here, it's 3 bytes. Now that's the reason why whenever you want to open a file, and this is something that if you do a bit of data science and download CSV files and so on, you all have been through this. You try to open the CSV file in a spreadsheet software, and then there's plenty of weird characters, like it should be an umlaut or umlaut, and it comes in a strange square root thing that is unreadable. This is what happens if you open with the wrong encoding, naturally, and this is why you need to select the proper encoding. The baseline here is nowadays, whenever you start a new program, a new startup, a new website, and so on, use ETF-8. Do not use any one of the other encodings anymore. This is the way to make yourself future-proof and already internationalizable. If you create the startup in one country, then you can translate to any language in the world in a straightforward way. That's the benefit of UTF-8. It's even better if you can even design your whole system that you already anticipate that it can also be right to left, like in Arabic and other languages, right? So this is called internationalization. Okay, so this is the UTF-8 encoding. So you see, even that is not trivial. Even just reading the files is not trivial. And what's not trivial also is how to detect the encoding. How do you know? You just find a document on the internet. Even just knowing what encoding it has is not trivial at all. There are a few tricks. One of the ways that maybe it's written inside. You start reading the document and you see it written inside. Another way is that the very first bits in there kind of give you a hint about that, and so on, right? So already that is a challenge. Supposed to move to the next slide. There you go. Nowadays, we also have new tools available. We could also use machine learning in order to automatically detect an encoding and so on. So there are other ways that are slowly appearing. But that was the easy part because it was text. So when it's text, at least you know that you are supposed to decode characters. The problem is that not everything is a text document. You might have a PDF, you might have, I don't know, maybe it's zipped. You have a zip file, a tar.gz, and so on and so on. So in that case, it's not even text and it's software-specific encoding. So it means you need to understand all of that. And that is not even simple because if you look in the very long term, it's kind of an unsolvable problem. Imagine people doing archaeology in 1,000 years and they find what we've been doing. They don't even have the tools anymore. How do you even open and read the documents, right? Just the content itself is not enough. You also need some extra information. This is in fact the reason why you know that there are journals dedicated to data. So data journals where you can publish data sets. And then you put the data somewhere else. The ETH library offers that. They allow you to update data sets to them, and they will act as a repository, and then you can commit the data paper to a journal. It's very interesting if you look at the requirements of the ETH library of what you can upload and what you cannot upload, because they are really very, very future-proof in the way of what they accept or not. They really have in mind that somebody very far away in the future might be trying to access that data set, but they no longer have some software we use today that is obvious, but you have no guarantee that it still exists in a century, right? Okay. Then you have some formats like XML, JSON that we are not covering in this lecture. We do it in big data, but here too, you might have some different ways to encode the character. So AMP is for the ampersand, LT, lower than, and so on. Then you have binary encodings. So here it's completely impossible to read without the actual software or driver that created the documents. Finally, there's the language, because as we will see, this linguistic post-processing or pre-processing that we do will depend on the language. And that changes a lot of things in the way you build your system. So when you parse the documents that you download, you want to identify the language. Is it English? Is it Mandarin? And so on and so on. So you want to identify the language, the encoding, the type of documents. And here again, machine learning kind of comes to the rescue to help you do that. I think you probably already experienced how easy it is for machine learning. Just if you use ChatGPT, you can type any language in there, it will just understand. So it's we know how to do these things today. Okay, that was the first challenge. Now the second challenge, I said earlier, we simplified by considering that the document is a book or maybe a PDF containing the book. Now, what you are indexing might not be a book. It could be an email archive. It could be your inbox, right? There is information retrieval software for your inbox. you might be indexing papers or a master's thesis or a PhD thesis, and then it's spread over multiple files. So what do you call a document? Is it inside? For example, you have a single email archive, but every email in there is a separate document. You don't want to treat your whole inbox as a single document. And the opposite way, should you treat some PhD thesis spread over 10 different files as a single document, right? So the granularity of the document is not so easy, right? If you consider, for example, LaTeX source. Okay, so that was for parsing the documents, figuring what a document is, figuring out what the encoding is, what language it is in, the type of document, and so on. When you have done that, you are at a point that you have the characters, you have the text, and you can start working on looking at it from a more abstract perspective in terms of terms. But there is still a lot of things that have to happen to reach that point. So now I assume we know the encoding, we know the language, and so on, and we are at that point that we have the characters. So I think these are the same four that we had last week. So what you can typically do if you think, imagine it's the first time you build a system, you're the first time in the world trying to do that. There is nothing that has been done before. So the first ideas that you might have is, for example, you throw away the punctuation, right? So you kind of separate with the spaces, but then there's a few commas and semicolon and point and so on. So you could think, okay, let's throw them away, right? And simplify. But that's already a first problem, because if you do that, you quickly realize that it doesn't always work. The first thing that could happen is that the point was actually part of an email address. And the email address, you probably do not want to actually tokenize. You want to have it in a single as a single token, and you want to preserve the point. A second aspect that is specific to the English language is that you have these compactions that you can do, right? Isn't instead of is not, right? So in that case, the apostrophe is not something you want to throw away, right? It's actually valuable information because this is the same as is not. Plus, here it's actually two words, but since you say isn't written like this, you don't have a space in there that helps you distinguish between the two. So that's another problem. Then you have the family names that can also contain special characters, like in here. Then in English, you have these dashes that you can use to bind words together as a single group. This is also not something you want to throw away. In German, it's, I was about to say easier, but actually it's more complex because you know that in German, you don't even have the dashes. You just put everything together. Then you don't have spaces in order to disentangle it. In English, what's interesting to know about the dashes is it's optional. Technically, there is no grammar rule that forces you to have or not have the dashes. The idea is just that it should make it more readable. So whenever it makes sense, you try to do it. For example, if you have an adjective and a word and you never put the dashes, if you have two words like a noun, 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 then there's no dashes needed. But in some other cases, over time, it gets attached like keyboard, doormat, and so on, right? So in English, you have, like in German, this way of putting the words together with no separation, but it takes a century or so to happen, typically. Today, for example, in the 19th century, today was written to-day. Tomorrow was written to-morrow. So if you look at 19th century literature, it was like this. Website, for example, kind of happened quicker, but I think things accelerate, but now you do find website written like this. Then you have the geographic name, right? If you have Canton Basel-Stadt, for example, you don't want to separate it. This is one single entity, right? So you see, even that is not trivial. How do you tokenize? What do you do with punctuation? And these are even more corner cases that you will find in the textbook of the lecture. You might have a company name, Hewlett-Packard, state-of-the-art co-education, the whole team back and drag him away, maneuver database in a single word, in two words. This is also one that happened quickly to have it in a single word. San Francisco, now it's the opposite. You have San and Francisco, but it's still the same city. Now, Los Angeles-based company. So here the dash is between Angeles and base, but Los Angeles actually belongs together, and the dash should actually separate it. Go figure, right? Same here with cheap San Francisco dash Los Angeles fares. And again, the dash is supposed to separate the two, and San Francisco is together and Los Angeles is together. Then you have similarities like York University versus New York University. And here it's one is a subset of another. So you have to figure this out when you parse. I told you it would be confusing, right? And what I want to show you is it's absolutely not as trivial as it seems. And imagine you want to build a Google knowing that this is the real world. This is what's actually going on. Then you have the numbers. You could throw them away, but maybe you want to index the dates. So the dates, the first problem is the convention. How do you know, for example, if 3/8 today, for example, the 8th of March, or could it be the 3rd of August if you write it in this way, right? So this is a matter of convention between the US and here. Then you have all of these ways that's not really standardized of writing down the dates like March 20th, 1991. Then you have the rooms. You have phone numbers that can have dots. In the US, you have the parentheses. In Switzerland, you have 3, 3, and 2 with spaces, but you still have people that also use the slash after the first 3 letters and so on and so on and so on, right? So it's really absolutely not trivial at all. So this is yet another issue. Now, another aspect is that in a language, the words have a life, right? They have, nouns can have a plural form, you can conjugate verbs, and so on. Now, in some cases, in English, it's easy, right? I would like a coffee, you would like a coffee. So in that case, it all looks the same. So would is just would, right? It doesn't depend on the person. But you know, in English, the third person isn't like that. We have a slide. Supposed to come. No? Yeah, there you go. So already that is the first problem, because here you want to consider want and wants to be the same, right? Semantically, if you try to do some search. But English kind of gives you an easy life because there is not so much change really, right? It's just a matter of adding an S. Now, there are other languages where it's even simpler than English. Do we have Swedish speakers? Yes. Okay. So here, jag skulle vilja ha en kaffe, du skulle vilja ha en kaffe. It's the same in exactly every tense. Here, it also means I would like some coffee, you probably guessed. Yeah, no, sorry, that was the French, the Swedish. So Swedish is easy because the conjugation is just the same for all the verb forms. So this one is easy. I like Swedish kind of has the vocabulary that resembles a bit of German. It has the simplicity of the conjugation of English, and it has kind of the sentence structure of the French. So I kind of like this nice way that it resembles the languages. Now, here I'm mentioning it because we will look at phonetics a bit later, but the third person plural, you can correct me, but I think it's pronounced dom, right? Instead, you don't say de, you say dom. So this is yet another example of how the pronunciation might not match the writing. In German, it does. In German, the pronunciation actually matches the way that it's written. Now, French is a catastrophe. You just have all of these conjugations and all these tenses and so on. So how do you even deal with all of that? And that's, I even managed to put a typo in there when I wrote. Who speaks French? Do we have Swiss Romand, French, Canadian, Québécois? No French speakers? Nobody speaks French here? Yes, awesome, okay. Now we have German. So German is a bit the same, that you have all of these conjugations. Ich möchte einen Kaffee, du möchtest einen Kaffee, and so on. But it also has the declinations, right? The fact that the words and the articles can change depending if it's the subject, the object. So you have this nominative, accusative, dative, genitive, and so on. And that's only 4. There are even languages that have 6 or 7 or even more than that. Okay, like the einen, for example. I assume most of you speak German, but the einen is because it's a subject. So the subject male form has an en in there, masculine form. Okay. And then I warned you that in German, you just paste it all together like this. So this is Donaudampfschifffahrt, Elektrizitäten, Hauptbetriebswerk, Bau, Unterbeamtengesellschaft. I think that's the World Guinness of Records. The longest word in German. I think it has roughly 80 letters in there. Who knew that word? It's kind of famous, right? And now go tokenize that, right? How do you separate it into all these components? I think it means for the non-German speakers, the society of the sub-officers or employees of the main business of the in electricity of the steam ships of the Donau, right? And you need to basically read it from the right to the left. So if you do it in French, for example, you would just invert it right to left, like completely invert it, right? Okay. What I never understood in German, especially when you're not a native speaker, is when you add an N or an S when you paste the words together. And apparently there is no rule for that. It's just done, and somehow it's intuitive to native speakers. Okay. Now comes Swiss German. Swiss German, I love that language, but it's not easy to learn first because you don't write it. So you need to actually learn it in the way you speak it. It kind of resembles German, but there are plenty of grammatical differences. For example, there is no past tense in Swiss German. You can, ich war, doesn't exist. You hear big C. In that case, ich hatte gedacht, ich Kaffee werde trinken. That's how you swap for some reason. So in German, you would say, ich habe gedacht, du hättest einen Kaffee trinken wollen, but you just swap it in Swiss German. Another example is that is notable. Etwas machen zu können, etwas können zu machen. That is also one that is swapped in this way. So you see, you have all of these particularities, and I think it might be mentioned in the book, but I think that Swiss German has a very strange particularity that is linked to the way you stack when you try to parse the language. I can't remember exactly the thing, but Swiss German breaks something compared to other languages, and I think it's the only language of the world that is like this because of the way that it organizes the order of the words. Something also interesting, actually, only figured it out after a few years that I was in Switzerland. You know that in subordinate clauses in German, you're supposed to put the verb at the end, right? So this is how you see when politicians do a Stack Overflow error when they don't remember the word they have to put at the end. But in Swiss German, apparently, the verb in subordinates comes in the third position. It's not like it's an explicit rule or something that many are aware of, but this is the reason why when you actually speak, you would start the subordinate. You would not put the verb in the first or second position because that would be ambiguous with a main clause, but you might maybe put the verb at the third position and then you continue with a few more words, right? And that's also a commonality of that language. Yeah, it's very fun to actually learn. Then we have Chinese. Do we have Mandarin speakers? None? All right. So this is Mandarin. So here, the difference with other languages like English or German is that we have many different characters, thousands of them. I think that this, in fact, is the only alphabet in the world that has survived from the very beginning. It has always been like that, and it was independently invented like this. It's the only one in the world. All of the alphabets that existed back then, they disappeared. What you see, and these actually Chinese students from a previous year that told me that this is the Wikipedia page basically that is on China. So it describes the country of China. they made me aware that, for example, it's just on Wikipedia, right? But in the alphabet, you have this simplified, this is probably what it is, you have this simplified alphabet that is kind of more convenient to write quickly, and then you have the traditional alphabet that is more involved. And every letter kind of exists in the two forms. In Chinese, you don't conjugate the tenses, so you don't have, like I showed you in French or German when you conjugate, it's just the verb. I think you don't even have past or future, you just add a word or an adverb that says yesterday, tomorrow, and then that takes care of the tense that you put in there. क्या इस कमरे में कोई हिंदी बोल सकता या सकती है? No Hindi speakers? Okay, I'll go quickly. So this is the Devanagari script. It's also beautiful. The difference with Chinese is that the number of letters is actually limited. I think it has between 50 and 60 different letters. So these are actually consonant and vowels. So this here, we try to read it, me is term achaparahahun. It means I will study well in this semester. The first thing you see is that the conjugation of the verb doesn't only depend on the I, you, he, she, we, and so on. It also depends on the gender. So when you speak, basically, a man would say raha, and a woman would say rahi, but this is the actual conjugation of the verb. It's the ing, studying, basically. I am studying. Then you have declinations, just like in German, but there's only two. There's it's called the oblique case. There is the main case and the oblique case. So this is to me, mir, muche. Information retrieval, Dahoud passant here. I like information retrieval. And here, this is the first person. So you do have the conjugation of the person and of the gender. What is interesting is that in Hindi, there is no present tense. It disappeared completely. So you have to use a special construct with the verb to be and what is called the habitual participle. And you have to do it that way. But the future exists. So you do have, like in French or in German, some future conjugation like this. Like unga and ungi is basically what you add in order to make it a future. All right. So maybe there are Hindi speakers on the watching YouTube, so that could interest you. Okay. Now there is another language that I would like to tell you about. Do we have any Siberian Yupik speakers? Nobody on the Zoom chat? Okay. So there is this, it took me some time to actually find it. I had to Google a bit. So what does negyak tuk yu guma yak petalu mean? This is actually a full sentence. So here the full sentence is actually in a single word. So if you want to translate it, neg means eat, yak tug means to go to, yug means want, uma is the past, yag some frustration, that you express. Pet is some inferential evidential, it kind of a way of saying it turns out that. This is the third person, and then you have alu, which means also. So now if you want to translate it, it translates to also, it turns out that he or she wanted to go eat it, but something. Yeah, the frustration part is in there. So there is actually a paper that investigates that language. But the reason I wanted to show it to you is that it breaks tokenization. How do you tokenize this thing? It's kind of similar to the Donau am Schifart word in German, but now you have the full sentence that is actually in a single word like this. Okay, I think it's a fun way to end the first hour. I hope you enjoyed it. The goal was to show you, like, with the diversity of languages in the world, how complex it is. I'll then go back to the, how to build the index and a bit of terminology in the second hour. So I'll see you in 15 minutes right after the break. Thank you very much.